One of the first things that started sending me down the whole lightning side quest was when I realized TE-4, ABYC TE-4 recommends bonding the lightning ground system to the electrical ground system. And that introduced a real concern about anodic wasting. Now, this isn't an anode, it's the lightning rod, but it's aluminum, so it's going to be our stand-in. For the concern I ran into to make sense, I think it's really important to have a proper fundamental understanding of what is galvanic action, what causes anodic wasting, why do we need sacrificial anodes on our boat. So while this video is part of the lightning series, it's going to focus almost exclusively on what galvanic action is at its core. And then at the end of the video, I'll tie in the concerns that it raised with the lightning protection system. So fundamentally, there's two different ways that we can have metal wasting on our boats. The most common one is galvanic action, and that's where you look at the relative nobility of the metals, and the least noble metals are going to lose their atoms to the sea, and the rate of that loss is relative to the surface area of the cathodes, the more noble metals, their total surface area in the water. There's a second type of galvanic action that I want to mention, but we're not going to go into in too much detail. That is induced galvanic action. Perhaps the most common example of an induced galvanic action is if you have, for example, the bilge wire that's going to your bilge pump. It's nicked, it's frayed, it's corroded. Somehow the current carrying conductor, copper, inside of the wire has leaked to the outside world. It's sitting in the bilge water is dirty, making it a really good conductor. Your keel bolts go through the bilge into your lead keel, and the lead keel is sitting in the water. In this case, the current leaking out of the wire leads to rapid wasting of the metals outside of the boat. You'll often see this when you go to check your anodes and they're just gone. That's all I'm going to say on induced galvanic action. It's a huge topic, all of its own. This video we're going to focus on chemical galvanic action. So what does it mean when we talk about a more noble metal, like the stainless steel prop shaft here, or a more anodic metal, like the aluminum air terminal in this hand? Now, in boats, we tend to refer to our sacrificial anodes as zincs. It's kind of like a Kleenex thing. These days, most sacrificial anodes are made out of aluminum, maybe manganese, maybe zinc, but mostly aluminum. For a metal to be considered anodic, the outer electrons in its valence shell, in its actual sea of electrons that are surrounding the metal latticework that makes up the aluminum bar, are in a high energy state, meaning they can be readily stripped away from the metal. A cathodic metal is a metal that has a stronger grip on the electrons in the valence shell. Its electrons are at a lower energy state. They're less willing to leave the metal. At its most simple, the moment I made contact between the aluminum and the stainless steel, there was a very, very brief, momentary exchange of current. You had electrons leave the aluminum and enter into the stainless steel. This is because the stainless steel has such a tight grip on its outer electrons. The protons in the nucleus have a very strong hold, relatively speaking, to the electrons in the valence shell, and that charge, that attraction, is still there, even though its valence shell is full. The moment I made the contact, some of the electrons flowed out of the loosely bonded electrons in that electron sea that makes up the valence electrons, and they were attracted to the lower energy state of the stainless steel, of the cathode. I think it was Feynman who said that if you think you understand quantum mechanics, you don't understand quantum mechanics. I know I don't understand quantum mechanics, meaning I really don't know what I'm talking about. But I'm going to do my best to explain why the different metals have different energy states, because this is core to understanding the whole galvanic action process. Most of us, when we learned about the atom in public school, we were shown a model that looked kind of like a solar system. You had the nucleus at the heart of the atom that was made up of neutrons and protons. How many? Depends which atom you were looking at. For however many protons you have in the nucleus, you have to have a corresponding number of electrons in the various orbitals. So we would often see it described as having one ring that might have 2 electrons and then a second ring that might have 4 electrons. How many rings, how many electrons per ring, depends very much on a per atom basis. But you get the idea. It looked kind of like orbits of planets around a solar system, around a sun at the center. That model was dramatically simplified for us being kids. In reality, electrons don't exist as a single particle zipping around the nucleus. It's not how it works. It actually exists as a probability cloud. The shape of the probability cloud of the electrons on the inner layers, the inner shells of the atom, can have different shapes. When you have a cathodic metal, you have the inner shells are shaped like they're bulbous. They don't make a tight form. I'm going to try to find some pictures of what they look like here because I'm doing a poor job explaining it. The result, though, is the inner electrons don't well shield the protons in the nucleus, meaning the attractive force that the protons put on the electrons that pull them in, that pull is not shielded, which is why they have a strong grip on the outer electrons. When you're dealing with more anodic metals, the shape of the probability clouds of those inner electrons is much more tightly packed. And what that does is it ends up acting like a Faraday cage. The attractive forces of the protons on the outer electrons is dampened because the shape of the electron orbitals in the lower shells acts like a shield, blocking that outward grip of those outer electrons, meaning the outer electrons can be stripped away much easier. There's less force holding them towards the nucleus of the atom. To any actual physicist that might see this, I am so sorry. That was the best I could do. So while I was trying to come to understand all of this, I had this idea for an analogy, and I think it's a useful analogy. I'm going to give it to you, and you can let me know in the comments below how good or how horrible this analogy is, but here we go. If I look at my anode as a water tower, I have this big tank of water, and it's sitting up in the air. It has gravitational potential energy. The water wants to come down. My cathode would be a neighborhood of houses and stores tied into that water tower. At the bottom of the water tower, I have a spigot that closes the valve, so it completely cuts off the entire community. When that valve is closed, it's like my anode and my cathode are like they're free. They're not touching each other. There's no way for the electrons, pretend I'm not here and I'm not holding them. There's no way for the electrons to get from the anode to the cathode. There's no way for the water to get down and out of the tower and into the community. The community is tied now into the water system, but all of the faucets and spigots of all of those buildings are turned off. When I take my anode and my cathode and I bond them, we do this in our boat with bonding wires, in the absence of an electrolyte, as if our boat was sitting on the hard stands, not in the water. The moment of the bond, it would be like opening that valve at the base of the water tower. There would be a very, very brief moment where some current would flow as it filled up all of the empty pipes, but very quickly, those pipes would fill up, back pressure would form, and the water would stop flowing. When I made the contact between the anode and the cathode, outside of the electrolyte, there was a very, very brief charge transfer. During that charge transfer, the anode became positively charged. It had a deficit of electrons. The cathode, the stainless steel, became negatively charged. It gained electrons. As it gains electrons and it starts to build up that charge, it creates the back pressure that stops any further flow of electrons out of the anode and into the cathode. Without an electrolyte, you have that very brief charging of the pipes and then nothing further happens. So for those of you who enjoyed physics class when you were in school, you're probably thinking this all sounds very much like a chemical battery. It is. Inside of a chemical battery, you have dissimilar metals. You have a cathode and you have an anode. And the distance on the galvanic series between those two metals represents the voltage. Now, you can stack them to increase the voltage, but let's just keep it simple and imagine we have an anode, we have a cathode, and inside of this case, there's an electrolyte. There's a chemical that allows for this reaction I'm about to describe. Now, one of the key differences between an actual battery in our boat, an actual battery, there's no connection between the anode and the cathode. Inside of our boats, it's like the battery is always short-circuited because we got the bonding wires connecting the prop shaft. The prop shaft is bonded to the bronze prop. You have the anodes that are bolted onto the prop shaft. If you have bronze through hulls, those are bonded, etc., etc. It's like I had a wire shorting this out. Now, with a battery, you would put a load between the positive and the negative, and that would allow current to flow from the anode to the cathode and do work as it's traveling. So at this point, I'm going to put the battery aside because the analogy starts to become a little bit less useful. So we know that by the nature of the energy potential of the valence electrons in the anode and the cathode, there is a natural desire for electrons to flow from one to the other. We understand that once the charge is transferred enough to create the back pressure, that the electron flow stops. Now, in our boat, we're sitting in water, typically salt water, which makes for an excellent electrolyte. But this is also true in fresh water and brackish water. Inside of that seawater is dissolved oxygen, O2. There's a lot more than that, but the one we're most interested in is water is H2O, but seawater is not just H2O. The dissolved oxygen, in combination with the H2O molecules, in combination with excess electrons on the prop shaft, when they come into contact with each other, a reduction reaction occurs. I'm putting it on screen here. The O2 molecules, in combination with two H2O molecules, in combination with 4 electrons on the surface of the cathode, undergo a reaction and they create 4 hydroxide ions. When this happens, those 4 electrons leave the cathode. As those 4 electrons leave the cathode, a little bit more space, the pressure has been reduced, and now the electrons can flow from the anode to the cathode. Returning to the water tank analogy, this would be similar to somebody opening up a tap and allowing some of the water out. They closed the tap, and that water that left the system dropped the pressure in the system, and so some of the water was able to come down out of the tank. Of course, we're not dealing with just one reduction reaction at a time. We're dealing with countless happening all the time. How fast? Depends on the total surface area of the cathodic metal in the water and how much dissolved oxygen is in that water. So now we understand how the electrons leave the cathode. The last piece of the puzzle is our anode. What happens here? So if you recall from the previous video, when we were talking about the negative electric field coming down from the cumulonimbus cloud, from the cloud that's likely going to strike our boat, that negative electric field had a repulsive force on our lightning rod. That repulsive force pushed the electrons either down or full on out of our air terminal. That left exposed atoms where the positive charge started to create its own positive electric field. Now, in the previous video, we talked about how that led towards streamers. St. Elmo's fire, the streamer that would go up and connect with the lightning's stepped leader that created the ion channel that led to the lightning strike. Blah. In this case, it's not that they're being pushed away, it's that they're being pulled away, but the result is the same. You have atoms of aluminum, or zinc, or manganese, or whatever metal is the most anodic, being exposed, creating a positive charge. Okay, what does this mean? H2O molecules are neutral in that there's an electron for all the protons. It's not an ion. However, an H2O molecule is a dipole. What this means is that though there is an electron for each proton, those electrons favor the oxygen side of the molecule. And that results in a net negative charge on the oxygen side and a net positive charge on the hydrogen side. This is the reason why water is such a good solvent. And we're going to talk about how it dissolves our anodes in the water. A single exposed aluminum atom will attract the oxygen side of one of the H2O molecules. It will connect oxygen pointing at the metal, and it's kind of like sticking a shovel in the ground. And your aluminum atom is like a rock in the ground. One shovel is not enough to pry it free. When you lose the electrons, you weaken the electrostatic force that's holding the aluminum atoms into the metal matrix. But weaker doesn't mean gone. It still has an attractive force that's holding that aluminum atom in. So one H2O molecule alone isn't enough to pry it out. 6 is. So what ends up happening is you have an array of 6 H2O molecules pointing at the exposed aluminum atom, the one that's missing an electron. The positive charge of the aluminum atom attracts the negative polarity of the H2O dipole, and they create a ring of 6 of these H2O molecules, and you can imagine it like 6 people with a shovel all around the rock, and they all pry together, and that's enough force to rip the aluminum atom out of the metal matrix. When that atom is stripped out, you end up with a new ion called hexaaqua aluminum. That goes off, it goes through a bit more chemical reaction, but the point is that the aluminum atom is physically removed from your anode. It has now just gotten a little bit smaller. For every reduction reaction that happens on the cathode, 4 electrons are stripped. Meaning, for every reduction reaction that happens on the cathode, we're going to lose 4 atoms from our anode. Returning to the water tower analogy. If you design the water tower so that it gets replenished faster than it gets drained, you have no problem. You size the community, the surface area of your cathode, such that the drain of the water tower is sustainable. Translating this back to our boat, the size of the water tank and how quickly it's refilled is a stand-in for how often we check our anodes and replace them. Replacing an anode is refilling the water tank. Okay, so now we understand how these waste. So how does this tie in then to the lightning system? When we design our lightning protection system, ABYC requires a minimum of 0.1 meters squared, which translates to 1 square foot. Now, that might sound like it's not very large. That is 0.1 square meter or 1 square foot. That was the minimum. For reasons I will explain later, I am adding this as well. And by later, I mean in another video. In an ideal world, we want to maintain a ratio of about 1 square centimeter or 1 square inch of anode for every 8 square centimeters or 8 square inches of cathode. At that ratio, you should be able to comfortably go a season between checking your anodes and you're fine. Again, assuming you don't have any induced galvanic corrosion, but that's a whole other story. So I'm sure that most of you have already seen the problem. If I directly bond my lightning ground system to my electrical ground system, I have just significantly increased the surface area for those reduction reactions to occur. Meaning, I am going to suddenly start wasting my anodes a lot faster. Now, I'm going to use the numbers from my boat, a 1981 CNC Landfall 38, as an example, and I'm going to use the numbers as she came from the manufacturer and as I'm setting it up for my electric conversion slash lightning protection. As she shipped from the factory, I had about 2.3 square meters of cathodic surface area for my anodes. I have a beehive type sacrificial anode that goes on the end of the prop, and I have one ball type that goes around the prop shaft. The combination of the beehive and one ball works out to about 290 centimeters squared, which gives me a ratio of 1 to 8.1, almost perfect. CNC knew what they were doing. When I tie in my lightning protection system into the electrical ground, the surface area jumps to 6.2 square meters. With the same one beehive and one ball, the ratio goes all the way up to 1 to 21. That means that my anodes are going to waste more than twice as fast as they would have before. Okay, so knowing this, we have two options to solve the problem. The first is add more balls. Be a grown-up. If I upgraded to have 3 ball type sacrificial anodes, which is about the limit of what I could fit where the exposed part of my prop shaft is, plus the beehive, I would be able to get the ratio down to 1 to 10. That is not ideal, but it's acceptable. So the simplest solution would be, okay, I'm just going to put 3 ball type plus 1 beehive type sacrificial anode, and I'm going to carry extra spares. And if you know that you need to do that, and you've done the math, and you know that that's going to last, or you don't know but you think, and then you check your anodes a lot more often, that's fine. That is a perfectly valid, completely sufficient solution to the problem. The second option, and this is the option I'm going for, I am going to create what's called a capacitor bridge. My capacitor bridge, and I'm going to go into a lot more detail in a dedicated video when I actually build it, is going to be 330 microfarad using large 6,000 volt capacitors in parallel. They're 22 microfarad each. I'm going to have 2 banks of TVS diodes, and I'm going to have a 40,000 volt gas discharge tube and a honking bleed resistor. Why, blah. I'm saying that now because I know some of you people are incredibly smart and you're going to be like, you can't just use a capacitor. I know. For the rest of this video, though, I'm just going to focus on the capacitor bank. The reason why a capacitor works as a good way to bond but not bond the lightning ground system to the electrical ground system is to a DC current, which is what galvanic action is. When you bond the lightning ground system to one side of the capacitor and you bond the electrical system to the other side of the capacitor, the cathode is going to cause an initial charge transfer towards the anodes. But the capacitors are going to charge up, and as soon as they charge up, they create back pressure. I'm simplifying, it's electric field, but then the current stops. And what that does is it electrically isolates the ground system of the lightning side from the ground system of the electrical side. I should take a brief moment and explain why we need to bond the lightning system to the electrical ground system in the first place. Because if you realize that the capacitor only allows a super brief little charge transfer and then blocks it and it acts like an open circuit for the rest of the time, how the hell does it solve the problem of ABYC wanting the ground systems bonded? To answer that question, we need to understand a couple things about lightning strike physics. When the streamer coming off of your mast, or ideally your air terminal, connects with the step leader and forms that plasma channel, at nearly the speed of light, about 30,000 amps worth of electrons dump into the top of your mast. Once it hits the top of your mast, it's going to take every path possible to reach the water. Now the current is going to divide between the different parallel pathways, and that division happens based on the inductance of each of the paths that determines what percentage is going to take which path. Again, another coming video. But for now, the key is you have this massive current at the top that is looking for all the ways to get to the ground. So I have 30,000 amps that effectively instantaneously appears at the top of the mast. My mast is about 15 meters. When you add the air terminal and a couple other things, it's closer to 17, but 15 is easier math. So we're going to say 15 meters. The metal has about an inductance of 1 microhenry per meter. So we're going to say that we have about 15 microhenries of inductance between the masthead and the lightning ground bar. From the inductance and from the current, the last thing we need to determine how many volts that translates to as a potential on the boat is the change of current over time. The mathematical formula is volts equals inductance times the change in current over the change in time. If you were able to have a magical oscilloscope that somehow could survive this, and you stuck one probe at the masthead, and you measured the current rise at that exact moment that the streamer connects and all of that current dumps, The current dumps that 30 kiloamps in about 1 microsecond. So to calculate the voltage that's going to appear on the boat, all of the lightning ground electrical system is going to rise to, you take 15 microhenry times 30,000 divided by 1 microsecond. I'm putting the formula on screen here. Because that instantaneous rise of 1 microsecond is so incredibly steep, it translates to 450,000 volts. To keep in mind, that is the IEC 62305 median strike. It can get up to 100 kiloamps or 200 kiloamps. So that 450,000 number is kind of arguably a little conservative and optimistic. The reason I say that is because, unlike lightning strikes over the ground, where there's lots of buildings and trees to discharge it before the current can build up too much in the cloud, out on the water, there's not as many things to send up a streamer, so the intensity tends to build. But again, I'm getting off topic. Okay, so if the backstay sitting right behind my head when I'm standing at the wheel of my boat suddenly rises to 450,000 volts, and the wheel I'm holding on to, which is part of the electrical ground system, is not bonded to the lightning system, it means that the backstay rises to 450,000 volts, the wheel I'm holding on to, which is basically a grounding rod because it's tied to my rudder and my rudder is sitting in the water, is sitting at 0 volts. Electricity can arc through the air in a laboratory at 30,000 volts per centimeter. However, when you're sitting at the helm of your boat, in the conditions where you would be struck by lightning, you are not in laboratory air. Because of the high humidity, the salinity, the resistance of the air to hold back the electricity is closer to 1 centimeter, can resist 5 to 10,000 volts. At 450,000 volts, that means that an arc can form up to 45 to 90 centimeters. Pause for dramatic effect. For all of you who've got a sailboat, I want you to imagine you're standing at your wheel and think about how close your backstay is to your head. Now, you hunter people, stop laughing. Non-such, I see you too. I'm using the backstay as the example, but really it's any conductor that is connected to the lightning ground system. So knowing then that the risk of a side flash is based on the voltage difference between two things, the steering wheel and the backstay, with you sitting in between it, made up of largely salt water, the risk becomes fairly obvious, I should imagine. So one of the most effective ways to reduce the risk of a side flash hitting you and killing you is to rise the voltage of the wheel at the same time. Now, you also want to bond your backstay. By bonding the backstay, you're able to drain out some of that current, meaning that it doesn't actually rise up to 450,000 volts. And now I'm going into a little bit more of the technical detail because of the parallel paths. The current doesn't all go down one particular path. So let me take the number I just used, 450,000 volts, and let's round it down to, say, 50,000 volts. So with a bonded backstay and the lightning system bonded to the electrical system, there's inductance of the bonding wires and whatnot. For round numbers, we're going to say the backstay rises to 50,000 volts and the wheel we're holding on to rises to 45,000 volts. At that point, the delta between the wheel we're holding on to and the backstay behind our head drops to a mere 5,000 volts. Now, 5,000 volts is nothing to sneeze at, but in the world of lightning strikes, that's nothing. It means that we need an air gap of about 1 centimeter to be safe from a side flash. Okay, we have almost all the parts. Last piece of the puzzle. Capacitors are effectively open circuits to DC current. They charge up and they sit there. They are effectively dead shorts to AC. Now, a lightning strike is, strictly speaking, a DC pulse of current. It's actually multiple because inside of a lightning strike you have the leading first stroke and then multiple secondary strokes. But that's, again, details for a future video. What matters to us right now is, from the perspective of the capacitor, as the current piles into the mast, it generates a massive voltage. From the perspective of our capacitor, that voltage rise is seen as a sudden massive inflow of electrons onto the lightning side of the capacitor. When those inflow of electrons hit that side of the capacitor, they generate a massive negative electric field. Now, recall again in our last video how electric fields push away electrons. So during that extremely fast rise, it looks like a high-frequency AC waveform. That creates a nearly equal push of electrons out the other side. Again, it's not actually AC because it's a singular event per stroke, but the result is that again, we're going to say 50,000 volts coming into the capacitor results in 49,000 volts being pushed out the other side for the duration of the waveform. But that's the only part we care about, because as the voltage drops on the lightning side of things, it can drop safely on the electrical side of things as well. So for that brief microseconds measured moment of a lightning strike, our lightning system bonds with our electrical system, meaning the voltage rise transfers through and we get the protective effect that led to ABYC TE-4 saying that you have to bond your electrical system and your lightning system. So let me finish up then by going back to that water tower analogy. If we take a second community and we tie it into the first community's water supply and we don't update the water tank, we don't increase its size, we don't refill it more often, then where the water was able to supply the needs of the first community without running out, you connect the second community and now the additional draw causes the water to diminish faster than it is refilled and you run out of water. The capacitor bank acts like a valve separating the two communities. Meaning, in an emergency, you could open up the valve and connect the second community to the first community's water supply. And as soon as the emergency is over, you close the valve back again. That's what our capacitor bank is. Okay, I am going to call it there because that was pretty info-dense. I hope this gives you, especially my fellow boaters, a better understanding of what's happening with galvanic corrosion and anodic wasting. But more, I really wanted to make sure that I gave the proper foundation to explain why me, a nobody who has no degree and no education, has decided to do something that goes against ABYC TE-4. I'm not saying I'm right, but I wanted to give the rationale behind the decisions I'm making. Okay, I'm the Digital Mermaid. If you found that not entirely too nerdy and you liked it, do the YouTube thingamajigs, please. And okay, bye!